So this is part 2 of computational thinking. Yesterday we went over it. It was quite a bit of stuff. So we're going to touch on it again, go over some of the basics, and then we're going to actually make things today. Talk a little bit about how you can use computational thinking techniques as part of your research when you're helping students make research projects. I'm going to show you some cool tools and utilities that have been created. And then we're going to build an interactive story inside of Scratch. So one more time, what is computational thinking? Computational thinking is a problem-solving process that includes a number of characteristics and dispositions. It's essential to creating computer applications, but also for general problem solving. And what we want to do, one more time, the decomposition, taking a problem and breaking it down into smaller pieces, more manageable pieces. Pattern recognition, observing patterns and trends, regularities that are happening within your data. Abstraction, identifying the general principles and then trying to generate the patterns. And then algorithm design, developing step-by-step instructions or programs that can run and solve these types of problems or similar ones. So let's look at this with subjects, right? Because I know it's very abstract. So breaking a problem into smaller parts or steps, if we look at literature. So with literature, it's breaking down the analysis of a poem into meter, into rhyme, into imagery, into structure, into tone, into diction, into meaning, right? When these are things that we're already doing in schools, right? When you learn poetry, we're learning about these different pieces, but that's also computational thinking. That's a piece of it, breaking down a problem into smaller pieces. We can look like recognize and find patterns or trends. In economics, we can find cycle patterns in the rise and the drop of the country's economy. So what are making things go up? What are making things going down? Is it purchasing? Is it something like COVID? If we look at the pandemic data and how it affected the economy. It's a good way to look at pattern recognition. Developing instructions to solve a problem or different steps. You can look at the culinary arts as a great example. Following a recipe to bake bread, following a recipe to do anything else. Also, generalizing patterns and trends into rules or principles or insights. We could look at chemistry, where we have to really find out the combination of elements in order to have some type of chemical reaction. And we can look at mathematics, figuring out rules and factoring for second-order polynomials. So computational thinking applies anywhere. Now, we had a good example of this. This is a smaller version of what we saw with Mr. Bongo's demonstration yesterday. So what I want you to do is we're going to do decomposition with these animals here. So I'm going to picture one of them. And you have 3 questions that you can ask to try to identify the correct animal. Is it a tree? Is it a goldfish? Is it a bear? Is it a bird? Is it a rooster? A tiger, a dolphin, or a flower? So if you can ask 3 questions, and you want to try to identify the one that I'm thinking of. So I'm thinking of one of these on the screen, and you can ask 3 questions to figure out which one that I'm thinking of.
So are you already eliminating the plants?
Oops. Yes, I did.
So the first question's already been answered for you. If you asked, is it an animal, the answer is yes, or had you asked, is it a plant, the answer would be no. So we know it is not the tree and not the sunflower. So 2 questions remain. Who wants to pick the next question to eliminate animals or creatures that are not fauna, not flora?
Yes. Does it live in water? No. The one I'm picturing does not live in water. It does not have wings. The question was, does it have wings? So we're breaking down the data into processes and problems and making it smaller, more manageable. So here's our problem. This is the data that we have. And then from the data, we start thinking of processes. The processes are our questions. How can we start eliminating pieces in order to find it? The problems into smaller pieces. So each question makes it a smaller sample. And it makes it a more manageable part because it starts becoming easier and easier to guess as you go through. So a lot of different types of questions you could ask. You could start off with, does it have stripes? If you said, does it have stripes? You would immediately say, yes. Well, then it's a tiger. Does it live in water? If you say yes, and we're still thinking of the tiger, I guess it would be no. We automatically eliminate the fish and the dolphin. And just going through that way, thinking of the different questions and breaking them down into smaller pieces. And that's the skill we want to teach our students within computational thinking. It's taking these large problems that can be intimidating. I think a lot of learners get intimidated when they're brought a problem that they don't understand fully, or they see a problem they think it's too much to handle, it's too big. And if you can teach them how to take a big problem and make it into smaller pieces, it becomes more attainable. It becomes an easier problem-solving process by breaking things down. So let's look at music. So music and computational thinking are also linked. You can use computational thinking for just about anything. So if we look at decomposition, we're looking at various parts of a song and dividing it into components, such as beats or notes, harmony, anything that you could examine, or you can examine each one of the pieces on its own. So if we play a song, we could listen to the beat and start trying to identify, if we say, what style of music is this? We could listen to the beat and say, well, if it sounds like hip hop, we know automatically it's not classical music, right? If it sounds like rock and roll, we can start eliminating just on the beat alone, and the notes as well. Then there's pattern recognition, where we can adjust each variable on the length of a note or the frequency of a note on a scale to get to the settings that you prefer. So when you think about music, all music is based on scales. We're going from C to C, C, D, E, F, G, A, B, C, all the way up. And all of those are patterns. So musicians, when they're trying to play with each other, the first question they want to figure out is, what key is this in? And if they can figure out the key, they know they know which notes that they can play. And that's a form of computational thinking, breaking it down into smaller pieces. So starting with the key. So they can hear the beat, they find the key, and then they can start playing together. Looking at abstraction or generalization, which is when you're adding, let's say you want to add a harmony. You have two people singing, and you want to add a third person to the singing. And that third person's going to start thinking about, what's the harmony? What are the notes that I could find in here that are going to sound good together? And then you start singing it. It's another form of computational thinking. It's that abstraction. And then the algorithm design. So a lot of music is actually designed by computers nowadays. If you see a music studio, that's mostly done by computer. So you can change the pitch, you can alter things, you can record somebody, you can edit, you can change pitches, change the scales, and add additional instruments. And that's all computational thinking in the end. And it's a good way to connect it with students. We can also look at the humanities. So the humanities, this is a type of research that can be done. So Google has a great tool called the Ngram. So what the Ngram does is Google, it's about 15, actually maybe 18 years ago, scanned as many books as they could find. And when they scanned the books, they put the words into their computer, into their natural language processing computer. And what they did is they made all of these books searchable by year and by word. So what this does, this is called an Ngram. And it looks at, this is a search term, Albert Einstein, Sherlock Holmes, Frankenstein. And you can type in words that you want to find inside of a book, and Google will do a search and say, from what year? So we can say from 1800 to the year 2000. How many times was the word Frankenstein looked for or mentioned in a book? And you can see it goes up, it goes up, it goes up, and then it shoots up really high in the 1960s. Around the 1960s is when Frankenstein as a movie and as comic books and became really big in pop culture in the United States. We could also look at Albert Einstein. So of course, Albert Einstein wasn't born up until this area, so he's not mentioned at all. And then he's born and starts getting mentions, and more and more and more. So you can start using these as a research method with your students if they want to look up, let's say they want to see when the pandemic started. Maybe in 10 years when the pandemic becomes history, right? When COVID becomes history and people have forgotten about it, or at least the children that are being born now, hopefully forget that this thing ever happened, right? And they go back and they say, what was this, when they have a school project and they're reading about this global pandemic? And you can say, well, use the Ngram and type in COVID-19. And you type that in and it's going to be 0000 up until 2019, 2020, and then you can see the spike that goes up, and then it'll probably start slowly going down. And that's how you can start looking at these historical trends inside of an Ngram, which is computational thinking, because it's taking a large problem, how many times has this word been said over time inside of books, and breaking it down into smaller pieces, and eventually using an algorithm, which is the search, and then putting it out into a output for you, which is an Ngram. So I want to give you a general overview of what Scratch is before we really dive into it. So Scratch is a visual programming language. And I know some of you have used Scratch before. If you've used Scratch, please raise your hand. Okay, so there's a couple of you. All right. So Scratch is a visual programming language. So usually when you, historically when you code, it's all by text. And you're typing text and it's like a language. But now what Scratch does is it makes it available for you to be able to code visually without having to learn all of the languages and learn the syntax of something. So this is what the interface looks like. You start off with a cat. This is your cat. So anything that you create over here, you're going to see it on this side of the screen. What Scratch also does, which is really neat, is it color codes everything. So you have these types of blocks of code. So these are called blocks of code. And these blocks of code can actually snap together like a jigsaw puzzle. So you have motion. So this says move 10 steps. And if you put move 10 steps, the cat will move 10 steps forward. You can say turn 15 degrees, and the cat will turn 15 degrees. Go to a random position. The cat will randomly appear somewhere on the screen. You can also type in coordinates, x, y, because in the end, this is just a grid. This is a grid with a x-axis and a y-axis. So you're basically using math here, except because it's visual, you don't see the math happening. And that's one of the great things that's fun about it, is you can have kids building things and using an x and a y-axis, and then you can debrief it later and then explain how they're using a graph and how they're using an x and y-axis in order to control the characters that they make. And that's another way to teach math through here. Here's some other pieces. So here's looks. We're going to go through each one of these. So looks, you can say hello for 2 seconds, which means when you touch the cat, it's going to say hello, and then hello is going to stay there for 2 seconds. But you can make it say anything. You can say, hi, my name is cat, for 2 seconds. And that's one way you can get these characters to start talking to each other. You can say, think, switch to a costume, because they have different costumes, which can make them look like cartoons as if they're walking. Change size by 10. Let's look at sound. So you can say, play the sound meow until it's done. So if you click it, it'll meow like a cat. And there's 100 different sounds that you can have here. You can start sound, you can change the pitch, change the volume. The next one are events. So you can say when the green flag is clicked, do something. So this is how you make things happen. So in Scratch, you always want to click the green flag in order to make something happen. You could say when the space bar is pressed, do something. So what we could do is combine the space bar mixed with move. So you say when we click the space bar, move 10 steps. And that's how you can start making short video games inside of Scratch, because this can be made to make video games. It can also be made to make stories. It can be used to make presentations. It can be used for all kinds of things. It's really up to your imagination. It's really popular in the United States to make Mother's Day cards. And children create interactive Mother's Day cards for their parents. And they'll send these to their mom and say, I love you, Mom. And you click on it, it plays little videos and songs, and really cute. And this is what the Scratch interface, when it all gets put together, looks like. So we can say, what you do is you grab these little pieces of code and you drag them to this side. And this is where all of your code goes. So you can see when the spacebar key is pressed, move 10 steps. Next costume, because the things have different costumes. Then it says, if touching sprite 2, then play sound cheer until done. So what that is doing, this is a race. This is a cat and this is a dog. This is the code that's going to be controlling the cat. So here it says when the green flag is clicked, and it has coordinates. Go to X 182, Y 49. So that cat is going to move to over here, which is what the coordinates are of this graph, of the grid. And then from there, when we hit the space bar, the cat's going to move 10 steps. It's going to switch costumes. When touching sprite 2, that's called this right here. That's the finish line. So you can see here there's a cat, there's the finish line, and there's a dog. So this finish line is going to have code that says sensing. And when it says sensing, it says when the cat touches the line, it's going to sense that the race is over, and the cat's going to meow. Let's say move 10 steps, switch costumes. If touching it, then play the sound cheer until it's done. And this is actually what we're going to build in the next couple of minutes. We're going to begin by creating a short race between a cat and a dog. And you're going to use your space bar to move the cat, and you're going to use your right arrow to move the dog. And they're going to race on this little screen. And you'll be able to code who wins, because in the end, this is how you'll decide who wins. If you want the dog to win, when you click the space bar, you might put move 11 steps. And the cat only gets 10 steps. So the dog's going to move a little more than the cat every time it gets touched. And what we're doing is we're identifying a sequence, the number of steps, the loops that are going to run, and so forth, and parallelism. But we'll get back to this after we start creating. So let's try it.